Hello everyone, I'm Dr. Samyukta S, Assistant Professor, Department of ECE at SJBIT. In this video, I'm going to explain you about a Verilog structural description. Okay, so before starting with, let me have a quick history of HTL. So HTL stands for Hardware Description Language. It is a programming language used to describe electronic circuits. Okay, popular HDLs are Verilog, VHDL, and System Verilog. Okay, so before HDL got evolved, engineers designed circuits manually. Large circuits require thousands of logic gates, because of which errors were common. So once the HDL got introduced, circuits are written as codes here, which is easy to simulate and it is easier to modify, and they developed the circuits very fast. So why we have to go for HDL? See, HDL allow engineers to describe hardware behavior, verify the design, and it simulate before manufacturing, and it will convert the design into FPGA or ASIC hardware. Okay, so the advantages of HDLs are it saves time and it reduces the errors and it supports complex digital system. Let me see the design methodology, which is the methodology we're going to follow in the HDL. Okay, so digital circuits are generally designed in the following steps. So the first step is the specification. So this specification defines the problem. Okay, so next step is the design. Design means we have to choose the design method, whether it may be a behavioral, data flow, or structural. Okay, so the next step is the coding, that is we have to write the Verilog code. So after writing the code, we have to simulate it. The simulation will going to check whether the circuit works correctly using a specific simulator. So after simulation, we have to do the synthesis. The synthesis will going to convert Verilog into actual logic gates here. Okay, so after synthesis, we have to implement that on FPGA or ASIC hardware. That is, the synthesized design is implemented on hardware. So these are the design steps or the design methodology that we're going to follow in the Verilog. Next, Verilog or HDL. So the features of Verilogs are, it is a case sensitive. Verilog is a case sensitive and it is one of the hardware description language. It is event driven and it supports concurrent execution and it is very easy to learn. Okay, coming to the applications, Verilog is used in multiplexers. It is used in adders, counters, flip-flops, registers, ALUs, processors, memory systems, etc. Okay, the advantages are it can be designed faster and it can be reusable, that is modules can be reusable, and debugging is easier, and fabrication has to be done before simulation. Let me have a Verilog introduction. So Verilog is a hardware description language used to design, model, simulate and test digital electronic circuits such as logic gates, flip-flops, counters, multiplexers, processors and memory systems. It allows engineers to describe how digital hardware should function before it is implemented on FPGA and ASIC. So as we all know, there are different Verilog description styles. There are different types of description in Verilog. So the descriptions are data flow description, structural descriptions, behavioral description, and also we have switch level description, and the mixed type description. So coming to the first description, that is the data flow description. The data flow modeling explains how data moves from inputs to outputs. See, instead of describing gates, we write Boolean equations here that defines the output. Okay, so the second type of description is the behavioral description. Behavioral modeling explains how the circuit behaves rather than how it is built. Okay, so here it uses always block and initial block to describe operation. So the next type of description is the structural description. The structural modeling describes the circuit by connecting logic gates here. It is similar to drawing a circuit diagram. The next type of description is the switch level description. Switch level description or switch level modeling describes the circuits using MOS transistor instead of logic gates. This is the lowest level of Verilog module actually. So next, the last type is the mixed type description. Mixed type modeling combines two or more modeling styles. For example, it will going to combine data flow plus behavioral or behavioral plus structure or structural plus switch level description. Okay, so most real world digital systems are mixed modeling because different parts of the designs are best described using different styles. So the advantage of this mixed level descriptions are that it is flexible, easier to design complex circuits, and it is very common in industry. Okay, so here we'll discuss about the structural description here. So here compositions of primitive gates to form more complex module. Here we use while declaration, means here by default identifiers are whiles here. So as an example, I have considered an Verilog program which is written for XOR gate here. So as we all know, XOR gate consists of two inputs, that is A and B, and one output, that is out. So the inputs and the outputs are defined here, and we have used the command such as while a bar, b bar, t1 and t2, by making use of which we are going to connect the gates. Okay, so the logic diagram consists of four gates, that is two inverters and two AND gates here. So the inverters are inverter A and inverter B, and the gates are AND gate 1 and AND gate 2 here. Along with that, we are using one OR gate. So we have defined the inputs and outputs of all the 5 gates within the bracket here. So we're going to connect each and every gate by making use of a identifier, that is wire. So this is another example I have considered, which is for full header. Here I have written the program by making use of a behavioral modeling as well as the structural modeling. The first one is the behavioral modeling. You can see that your module name is full adder, and within the bracket I have defined all the inputs as well as the output. As we all know, the full adder consists of three inputs A, B and C in, and two outputs, that is sum and carry, that is S and C out here. So input and outputs are defined. After that, here we have used the command that is assign in the behavioral modeling. So sum output is equal to A XOR B XOR C in and N modeling. Similarly, in the structural certain modeling is based on gate instantiation. So I've already told you that here we're going to describe the gate here. So module name is adder 4. Within the bracket we have defined all the inputs as well as the output of a full adder. So the wires we have taken as C1, C2 and C3, and we have considered FA1, FA0, FA1, FA2 and FA3 here. So within the bracket we have initialized all the variables and we have ended up with a